All right, now that we've talked about EMR and light and what exactly that is, we want to talk about the qualities of light, specifically the wave qualities of light and how we know that it's a wave. So the first one we want to talk about is reflection, because obviously light does reflect. That's how you see your image in a mirror. And that does tell us that it is acting as a wave. So of course, reflection occurs when a wave reaches a boundary between two media, and some or all the waves back bounce into the first medium. So for example, you look at the mirror, all the waves are bouncing back into the air in front of it and going to your eyes where you can perceive your reflection. But sometimes it could be like something like a window as well, where some of those light waves obviously go through, but you can still see a slight imprint or reflection of yourself in the window. So if the second medium is very rigid compared to the first, then most of the wave energy is reflected. So example, if your light waves are incident upon metal, then the reflected wave has almost the full intensity of the incoming wave. So if you look at a piece of metal, you'll see most of your reflection back in that. If the second medium isn't as rigid, then only some of the energy is reflected. So this is when your light waves are incident upon glass, water, things like that. So we have some wave energy being transmitted through the glass or through the water, but then some of it's also reflected back to you, which is why you don't see as good of a reflection of yourself in glass or water. So the law of reflection, it's really nice and easy, and that's that the angle of incidence is equal to the angle of reflection. So the biggest thing here is knowing some of the terms, and namely the angle of incidence. Okay, this guy right here is the angle of incidence. So it always has to be the angle made with this thing called the normal right here. And what is the normal? The normal is the line that is perpendicular to the reflecting surface. So that's what the normal is. So the angle of incidence is the angle that the incident ray, or the ray incoming, makes with the normal. So that's right there. And then of course we have our reflected ray, and it reflects off at the exact same angle. Okay, so we just draw these as straight line rays, even though they are traveling as waves, but that would just get too messy. And of course, angles have to be measured with respect to the normal here. That's just so important. I cannot stress that enough. Okay, so if you are given an angle of incidence, but it doesn't mark it on the diagram for you, you always have to know that is the angle being made with the normal. Okay, and if you're ever given this angle, then you will need to subtract from 90 to get the angle of incidence right here. We really need that guy. Okay, but that's really nice. So that just means when things are reflecting on a nice flat surface, they're going to reflect off at the exact same angle, which is pretty fantastic. But then we have something like specular reflection. So that occurs when light is incident upon a smooth surface. Okay, so single incoming direction, single outgoing direction, that's what this is. Okay, so that's you looking into a mirror, for example. Okay, but diffuse reflection, that's what makes diamonds all pretty and shiny. And that's when light is incident upon a rough surface, so it's reflected in a lot of different directions, right? So specular reflection right here is just nice, flat, smooth surface. But if we have a rough surface with a bunch of different flat sides, then the light is going to reflect in a bunch of different directions. And so that's why a cut of a diamond is so important, because it's all about the cut that makes it reflect light in the most because it's not necessarily about the diamond, because diamond's already really reflective, but it's all about how it's cut, because if it's cut in the right way, then it'll reflect even more light, and that's what makes it sparkly and shiny, and people go crazy over that. Even though a lot of other gemstones do that, but that's another story for another time, or for a social class, or something like that. So that's reflection. It's really, really easy. It's something that you've noticed since you were, born. So reflection is pretty nice and straightforward. Now let's go on to refraction, probably another phenomena that you have seen before, but you just don't look at as much, or doesn't kind of mess you up as much. Not mess you up, but it just doesn't impact you as much. And that is refraction. So that's basically just the bending of light of a wave as it passes from one medium to another. So you've probably seen this before. You put a straw in a drink and the straw looks like it's broken, looks like it's bending, right? When you look at it from the side, when it goes from the air to the water. And that's just because the speed of light waves are different in water than they are in air, than they are in glass, for example, as well. So even if you look at glass through the side where you have water, and then you see it going through glass, and then you just see it going through air, then it can even have 3 bends in it. So yeah, that's pretty interesting, but that's what that is. That's called refraction, where it looks like something bends because it's just the wave has a different speed in a different medium because it's passing from one medium to another. Okay, so again, just a little bit of housekeeping here. We have our incident ray right here. And of course, this is your angle of incidence because it always has to be made with the normal. So the normal, here's our boundary between the 2 mediums. Okay, and so of course the normal is perpendicular to that boundary. So that's the normal, and then we always need our angle of incidence here to be made with the normal. Okay, so that's really, really important. And then we have our angle of refraction. Instead of reflection here, we have the angle of refraction, also made with the normal. Okay, so make sure that you're always looking at the angles made with the normal. I am going to trick you. I'll tell you right now, I promise, I'm going to give you a question where I give you this angle, which is not the angle of incidence, and you're going to have to find the angle of incidence. What do? You just take 90 and subtract this angle from it, and then you get the angle of incidence. Okay? It's going to happen. I'm going to try and trick you, so don't let me. Remember, you always need the angle being made with the normal. Okay, so the index of refraction for light. So that's something that we use to describe different substances, different mediums that light will go through. Okay, so the index of refraction is N is equal to C over V. So N is what we're going to call our index of refraction here. So C is obviously speed of light in a vacuum. That's 3 times 10 to the 8 meters per second. And we're going to say that that's the speed of light in air as well. And V is the speed of light in the material. So for example, if it's going through water, it's going slower in water. It's going slower, less than 3 times 10 to the 8 meters per second. Okay, so that's what we call an index of refraction, N. So some common values is air is equal to 1, right? Because it'd be 3 times 10 to the 8 divided by 3 times 10 to the 8. So this is really the only one you need to memorize because, well, it's 1. Like, there's no ratio there. Or it's a 1-to-1 ratio. These ones you don't have to memorize. I'll always give you the indices of refractions for the specific things. But here's one for water, 1.33, and for glass. It depends on the glass. Glass changes from, glass to glass, but it's usually around 1.5. So those are just some common values, but not ones that you have to memorize. So we can calculate these angles or these indices of refraction or the speed it goes through certain things or the wavelength using something called Snell's law. Okay, so it looks a little something like this. This is on your data sheet under waves. And so with one of these things, I know these equations look kind of crazy because it's like, why is there 3 equal signs? So basically, you're just always choosing 2 things to equal. So if you have the angles of incidence and refraction and you're trying to find the speed through something else, then you just take this guy and make it equal to this guy, right? If you have the angles and you are looking for the indices of refraction, you have one of them, but you need the other, then you make that equal to that. So in this kind of equation, you're just taking one thing and making it equal to the other, right? Depends on what you're working with. So if I have the indices of refraction and the velocities, or at least one of the 2 velocities, then I'm going to choose those two. So you just choose any two parts of Snell's law that's going to help you in the specific question that's being asked. All right, and so these 1 and 2s are basically where 1 is the incident side and 2 is the refracted side. Obviously, the theta is the angle between the ray and normal, and its index of refraction. V is the velocity of the wave in the material, and lambda is the wavelength in the material. So notice all the 1s and 2s kind of line up except for the indices of refraction. The indices of refractions are the only ones that's flipped, so everything is 1 over 2, 1 over 2, or incident over refracted, except for the indices of refraction. But remember, you don't actually have to remember that. You have the equation in front of you. So really important to note, the frequency does not change when going from one to the other. Okay, frequency stays the same because frequency just can't change. Either your speed of the light in the thing is changing, or your wavelength is changing, but frequency is dependent on the wave source only. So if you have red light going from one thing to another, it's going to remain red light. So remember, frequency actually depends, or frequency defines what kind of light you have. So that's really important. So frequency does actually stay the same. So an example of this that doesn't have to do with light, but that anybody who has mowed a lawn has probably experienced before. If you ever need to take the mower onto the sidewalk to turn it around, you'll notice that it'll pull in a certain way. So if you're going from the sidewalk here to the grass, it will actually refract closer to the normal. And if you go the other way, where you're going from the grass onto the sidewalk, it'll actually bend away from the normal. And this is just because, guess what? The lawnmower going at a certain speed is going from one medium to another, and that refracts the angle at which it's going, which is an interesting example of that. I just think that's cool. So when light is moving from a fast to a slow substance, it bends towards the normal. So for example, if this was air and if this was water, right? Because we know that light is faster in air than it is in water. So that is when it will bend towards the normal and you'll get a smaller angle of refraction. And then when it moves from slow to fast, obviously the opposite happens. So say now it's going from water to air. It will always bend away from the normal. So this angle will always be greater than the angle of incidence. There's something called a critical angle, and that is the angle of incidence which results in a refracted angle being 90 degrees. So then it's what happens where you have something going in here, and then this reflects right along the boundary line. Okay, so of course it's only possible if traveling from slow to fast. Can't be fast to slow because that's always just going to go towards the normal. So we need it to be going towards the boundary. So of course that only happens when you go from slow to a fast substance. Okay. So here's an example here where we are going from glass to air. Glass is slower than air. And the incident ray, once it's at a certain angle and it refracts right here along the boundary, that's called the critical angle. So for this exact glass-air interface, the critical angle is 42 degrees. So if we're ever looking for that critical angle, again, we're just going to use Snell's law. But we want to look for this critical angle, but we know that the angle it goes through the fast medium is just going to be 90 degrees. Sine of 90 degrees is 1. And then we can line that up with either the velocities in that material or the indices of refraction in that material to figure out what that critical angle is. So if a question ever asks you for what is the critical angle, it's not going to outright say, well, then this is sine of 90 degrees, because that's what you need to know. You need to know that, therefore, the angle through the faster material is going to be 90 degrees. So let's do a few examples using Snell's law. Okay, so first I want to determine the critical angle for an air-water interface. Okay, so obviously I know I need to be going from air to water. So there's my beautiful little water. So here's my air, here's my water. Okay. So let's imagine that we have our critical angle there like that, or sorry, not our critical angle, or angle of incidence. Then we know what's going to happen if we have our critical angle, that in the air, that light ray is going to go at a perfect 90-degree angle. And so that's your angle of refraction. So, well, what else do I know? I know that index of refraction in water is 1.33. Wasn't given here because I just didn't need to, but again, it will be given to you. And the index of refraction has no unit or anything like that. We know the index of refraction for air is 1, which is nice and easy. So we know that light travels slower in water because the index of refraction for water is bigger. So the bigger the index of refraction, the slower it actually moves in that substance. Okay, let's set up Snell's law. Now, the nice thing about Snell's law is I don't necessarily have to have a specific order. So I can just say water and air. And then for the indices of refraction, just remember that's the one where it's flipped around. So the index of refraction for air divided by the index of refraction for water is what we should have. And of course, I'm looking for an angle. I have the indices of refraction. So those are the only two parts of Snell's law that I need to use right now. So I want to find the angle that it makes in water. That's my angle of incidence. And I know the angle it makes in air is 90 degrees because that's what a critical angle is. So if I want to find the angle in water, of course, that's just index of refraction in air times the sine of the angle it makes in air, which is 90 degrees, divided by the index of refraction for water. Okay, so the angle it makes in water is the inverse sine. Of course, index of refraction in air, 1.00 times sine of 90, which is also 1. So that's our whole numerator actually just turns out to be 1. And that's divided by 1.33, which is the index of refraction in air. Okay, and take the inverse sine of that to get the angle in water, or the critical angle is what we're going to get here. And that ends up being 48.8 degrees. I know I didn't technically have any significant digits given in the question, but our indices of refraction are pretty much always given to 3 significant digits, so that's what I took. And there we go. There is the critical angle for an air-water interface. This is another example, and it's usually there for me to warn people and warn grade 12s that you need to bring a protractor to your diploma. So that doesn't apply to you guys right now, but again, will apply to future people in the future writing diplomas. So I'm still going to do this example. But you could be expected to measure angles using a protractor, because this is an old diploma question where you have a ray of light traveling from water into an unknown medium. So we want to know, what is the index of refraction for the second medium? That's what we would like to know here. Okay, so basically it's going from here. So here's our angle of incidence to here, and there is our angle of refraction. Okay, so yes, you were actually expected, if you write the diploma, to bring a protractor to it. If you don't, guess what? That's okay, because you're smarter than that. You can also just measure these two things, or if you want to measure the hypotenuse, you can, but you can do that and then find that angle as well using tan. Okay, but if you want to do the hypotenuse, you can use sine or cosine or something like that as well. But if you just measure it, you should get an angle of incidence being the angle that we have in water, which is 40 degrees. Okay, and the angle of refraction, which is the angle it makes in the unknown substance is 32 degrees. Okay? So we use Snell's law. Index of refraction, the unknown substance, divided by the index of refraction, water. That's what we know should equal to, remember, the indices of refraction are the only ones that are ever switched. So then I have the angle of water that makes in water on top and the angle it makes in the unknown substance on the bottom. Okay, so I'm looking for the indice of refraction or the index of refraction in the unknown substance. So index of refraction in water times sine of theta in water divided by sine of theta in the unknown substance is what's going to get me that. So if you type that into your calculator, you should get the index of refraction of the unknown substance to be 1.61. And there we go. So just an interesting extra step, but one that if you're writing an online quiz or test, don't worry, I will give you angles, okay? I won't expect you to try to measure on your device, whatever it is that you're going to be using. Okay. One last thing I want to go over is total internal reflection. So this is what happens when an angle of incidence is exceeding the critical angle, because what's going to happen, it can't go at 90 degrees anymore. And so of course the light just like reflects right back into the slow medium. It doesn't even continue to pass through the fast medium. It just completely bounces back. Okay, so here we have our critical angle, and then if we exceed that, then it's just going to completely reflect on this boundary. It's not even going to go into the second medium. So that is total internal reflection. Okay, so you're always looking for if something is beyond the critical angle, then therefore it's going to reflect back. So this is, for example, if you set up Snell's law for this, it just wouldn't work out. You'd get an unknown or an error on your calculator. You'd try to find the angle that it's refracting in, and you would just get an error. So if you ever see that, then you just have to prove that it is beyond the critical angle. So you just find the critical angle and you say, oh yeah, well that's beyond the critical angle. So obviously it's just going to have total internal reflection. So that's that. So I just have one awesome example of this that you guys probably never even knew was an example of total internal reflection. So have you ever been in this situation where on a really nice hot day, which, oh my goodness, isn't that nice to think about right now, I wish, on a hot day you're driving and you see the road ahead of you and it looks wet. And you're like, what's that all about? It's like a hot, dry day. Why does it look wet? And then you get there and it doesn't look wet anymore. But then the road in front of you still looks wet. What the heck is happening? This is total internal reflection. So that's because the air just above the road is hotter than the air higher up, because obviously it's giving off a lot of heat. And cool air is slower, so therefore the light coming from the sun is going from a slow medium to a faster medium, and if it goes at a certain angle that's beyond the critical angle with reference to your eye, then the light totally internally reflects when it heads from the cool air to the hot air. So all you're doing is you're seeing the reflection of the sky on the road, and that's why it looks wet. And that's why, like, then you get there and it's not wet anymore, but then the stuff in front of you is wet because it's all about the angle that you're looking at it from. So obviously the road right in front of you, you are now smaller than the critical angle from that road, looking at that road, so you're fine, but then you look ahead and that's where you exceed the critical angle. So there you go. That's how mirages work. Let's do one more example where we maybe might have a critical angle. So here I have three interfaces. I want to determine the angle that light leaves the quartz water interface. Okay, so that's this interface right here. There's quartz and water. So I want to know the angle it's leaving that quartz water interface. Okay. And we have all the indices of refraction that we need for diamond, quartz, and water. So let's start finding angles of refraction. So we know since quartz is faster than diamond, it's going slow to fast, it's going to bend away from the normal. So it's going to look something like that. So first I'm going to try and look for that angle. Okay, so I'm looking at the diamond quartz first, because then that's going to help me find this angle, because I know I need to know the angle it's going out like that at, right? So this angle and this angle will be the same. So that's what I need to figure out. So let's do this where we have sine of the angle in quartz divided by the sine of the angle in diamond. And of course our indices of refraction are always switched. So that's the index of refraction of diamond divided by the index of refraction of quartz. So we're going to try to find this angle that it goes through quartz, because obviously we do have the angle that it's going through the diamond, and that's at a 35-degree angle of incidence. So angle going through quartz here. I'm just going to go, right to this. So inverse sine of this. So this is the equation you should get. If I could write it nicely, that'd be great. Okay, plug all those numbers in. So diamond is 2.42, so it's really slow, times sine of 35 divided by sine, oh, what am I doing here? I did that wrong. That's definitely not correct. Rather have the index of refraction of quartz down here. That would make a lot more sense. Sorry, guys. Okay, and that will be 1.46. Okay, so I get this angle of refraction for quartz being 72 degrees. Okay, so there we go. That is the angle that it's reflecting here at. So that's 72 degrees. Okay, which means that this guy is also 72 degrees. So now I need to figure out the angle that goes into this quartz water interface, because I want to now know what's this angle going to be right there. So now I flip to looking at quartz and water, and again using Snell's law with angles and indices of refraction. Okay, so again I'm trying to look for the angle in water, so I'm going to put that on the top. Divide that by the sine of the angle in quartz. And of course, our indices of refraction are switched there. Okay, so I find that angle in quartz. And guess what that gets us? It gets us a big old error. Why the heck is that happening? Well, that's probably happening because I'm guessing that 72 degrees is beyond the critical angle. So it's not refracting into here at all. So it's not refracting into here at all. What's actually happening is it's going back here at a 72-degree angle, because that's what's happening with total internal reflection. We know then reflection bounces back at the same angle. So that's actually what should be happening here. But it's not enough just to leave it there. You actually have to prove it. So I do need to find the critical angle between the quartz water interface right here in order to prove that 72 is greater than that. So let's do that really quickly, and then I promise I'm done. Okay, so we want to find out what's the critical angle between that air-water interface. Of course, the critical angle will be the angle in quartz, and then therefore the angle going through water will be that 90-degree angle. Okay, so let's figure out this critical angle that makes it go through water at 90 degrees. So remember, water index of refraction is 1.33, and then this is going to be sine of 90 degrees, because that's what the critical angle is. It's whatever it makes it go through the faster substance at a 90-degree angle. Divide that by 1.46, which is the index of refraction for quartz, and we get this critical angle of 66 degrees. So that is definitely proving to us that 72 degrees is obviously greater, and that's why there would definitely be total internal refraction. So since the angle in quartz is greater than the critical angle, then we have total internal reflection. TIR is just what we call it, because of course, who wants to, write more than that? So there we go. So therefore, we do know that it's reflecting back at that 72-degree angle. Okay, so that's what happens in total internal reflection. So if you ever see this error thingy right here, it's just showing you that it's likely beyond the critical angle, and therefore you have total internal reflection. So that's that. That is reflection and refraction and how that all works. And now I'm just going to assign you a bunch of questions so you can just practice Snell's law over and over and over.